Great to see such an energized and enthusiastic crowd this Friday afternoon. And I look forward to presenting rapid application prototype development with Cerebras inferencing solution. To introduce myself, I'm Lakshmi Ramachandran. I head up the Cerebras office in India, and me and my colleague will present this to you today. Can you move the slide, please? Welcome to this session. For those of you who haven't heard of Cerebras, we're a 10-year-old wafer-scale company. The company started in Sunnyvale in 2016 in India about 3.5 years ago. We develop both hardware and software. We are an AI supercompute accelerator company, which means we have a wafer-scale compute, which is in stark contrast to the wafer getting cut into chips, and then you derive a GPU or an ASIC from it. So we keep the wafer as it is, and this technology has been made viable by Cerebras for the first time on the planet. There's no other real wafer-scale compute. So why is this important for app development and inference? We'll go through that in this presentation. The Cerebras wafer-scale engine would have unique problems of thermal and cooling requirements, which were all solved. And so from a wafer-scale company, we became a systems company. And then we grew to data centers, setting up data centers, clusters of compute. The compute power on this is so high. This is about 1 million cores. And there is on-chip bandwidth of about petabytes per second and proportional memory. So it can do what thousands and thousands of GPUs can do with just one wafer, which is a dinner plate-sized chip. Why is this important for GenAI revolution? We are in the midst of a GenAI revolution where almost all workflows, enterprise or otherwise, have changed to using GenAI tools. We need fast inference to deliver content, to create content, to summarize decision-making, agentic automation, as we saw in the previous presentation. All kinds of use cases are now using AI to both accelerate as well as create new markets. What could be some of the app developers' challenges? How many of you have found speed to be a challenge when you're developing applications? The speed at which you get responses. How many of you have a challenge with speed? Yeah, this is the most obvious and most important challenge that we need to really make this viable. How many of you want more intelligent results? Everyone, right? Even if you're not raising your hand, I'm assuming you do. The third thing that keeps us from accessing this and using this is accessibility to compute, both hardware and software. Access to clusters, easy access to it, price effective, and easy to use APIs. This is what any developer wants. And finally, last but not the least, reliability or uptime. You don't want the cloud or the cluster going down too soon or too often when you're developing your applications. Let's see how Cerebras meets each of these challenges in a unique way. With respect to speed, Cerebras achieves the fastest inferencing solution in the world. We are 20x, sometimes 30x, of the nearest competition, whether it's a GPU cluster or otherwise. And this cannot be improved through any other technology with any number of chips. It's not about the number of chips. It is about the type of chip. In this case, you have on-wafer memory of 45 gig. You have petabytes per second bandwidth, and you have 1 million cores to parallelize compute. It's not like any other. We've been benchmarked by artificial analysis. It's the third-party organization that does benchmarking on AI products for various workloads and use cases. You can look us up on LinkedIn. So according to them, Cerebras inference is the fastest on most world-class models. Now, why is this important again? Let's break this down a little bit. Faster inference actually means more tokens per second. We all want more tokens per second, right? As you give your prompt, which is now of the order of 128K or even more, we have large prompts. And as you do fast inference, you get back tokens as generated output extremely fast. Now, the nature of inference is such that in a large language model, which has many, many layers of compute, every token that you want to predict, it has to go through the entire neural network, every layer, and finally you get one word out. That word is fed back to the beginning to generate the next one. So that's why it cannot be parallelized. The LLM's workflow cannot be parallelized, and that's why you need huge chips. It is sequential. Now, more tokens per second means that you can also get more insightful, more intelligent outputs. Who doesn't want that? So obviously, Cerebras comes in here, and faster inference means more intelligent results in a shorter time. If time is limited and you don't have as fast a chip, then there's a limit to how good a result you can have. It's not only the throughput. So more intelligence, more speed. I'd like to show you a demo of one of our recently published models. This is Qwen. Everybody's heard of Qwen? Yes, this is Qwen. And we show you side by side against a GPU-based cluster and on Cerebras system how fast the output is. This is to implement, this is the prompt, implement a Tetris game in Python. On the left is Cerebras system. It's already done at a blazing fast 2,600 tokens per second. And the other one on the GPU cloud is also done, but after some time. So you can imagine the productivity of your workflows if you're using Cerebras inference, whether it's for coding, to develop agents, agentic workflows, what have you. And this scale is true for pretty much all models. Let's look at this a little deeper. Most models, most state-of-the-art models nowadays are reasoning models. Why is reasoning important? It's not just a generative model. It executes a lot of steps before it can actually come up with the answer. If you've used Perplexity, you can see what it's actually doing. You can see the steps it takes to reason and come up with the answer. So it requires hundreds to thousands of times more tokens, because what comes out needs to be fed again, and then you split the whole thing into subtasks. All the latest models from OpenAI, DeepSeek, Grok, Gemini, they are all reasoning models, as most of you know. A simple one-shot inference where you give a prompt, get an output, just a simple question and answer. Let's say it takes X tokens. This represents just a single short inference. Now, reasoning models, how are they different from this? A reasoning model would build a plan, like you want to build a travel itinerary and book tickets, or you want to organize your email, or you want to clean up your entire folder according to some specific rules you give, whatever it may be. The reasoning model builds a plan, it breaks the problem down, it solves each of them one by one, and then collates and synthesizes the answers together before it gives you a proper, meaningful output. So this is one reasoning flow, which takes 10x the number of tokens. And if you're building agentic workflow with reasoning, then you have multiple subproblems, and there are multiple such reasoning flows, which could take 100x more tokens. And in a specific amount of time, if you want 100x tokens, you need really, really fast compute for you to do anything meaningful. With a slower system, something like this, you'd be waiting for hours or days to get the output. Why are some people still using non-reasoning models? As it turns out, The answer is speed most of the time. People avoid using reasoning models because they don't have access to fast, reliable clouds that can provide this. As of this week, we have Qwen 3 model family. And this is the artificial analysis comparison of output speed. You can see all the GPU-based solutions from the various AI hardware providers over here. And you can see Cerebras on the left. There is no comparison in the magnitude, and that's because of the fundamental architecture in hardware and software that we have based on wafer scale. A couple of days back, as you know, OpenAI announced the GPT open source model, 120 billion. And within a few hours, it was up on Cerebras inference service at a speed of 3,000 tokens per second. It's unmatched, and we don't believe it will be anytime soon to come. This speed creates possibilities for almost every vertical. The 10x inference speed or 20x inference speed helps you dream about different workflows that you didn't even think are possible. If you're probably having chai while coding, before you finish your chai, your code will be done. That's the speed we're talking about. What models do we serve? We have all the latest. This is not exhaustive. You can go to our website and look at them. We serve almost all the state-of-the-art models, all at similar speeds, and very competitively priced. It's easy to access. We talked about accessibility. It's very easy to access, has standard interfaces. Our APIs are OpenAI compatible. So if you've been building on OpenAI APIs, you can onboard on a Cerebras system in no time. So we are almost the same as them. Where are we hosted? We have all kinds of models, basically serverless API. If you're an app developer, you can use serverless API. We've hosted it on private clouds. We've also opened to on-prem deployment. We have done this in some places in the US. So for this to happen, the wafer scale chip is basically housed in a system. This system engineering is Cerebras' unique solution. It's our invention that makes wafer scale possible. So this system is put into racks alongside host machines, alongside switches and network cables, and that constitutes a rack. So a number of these racks form our data center, and there are data centers all over the US. We also have smaller clusters in several places in Europe and other places. We have a growing capacity for the growing demand. So we started off in a few places in the US with our previous generation, which is called Conda Galaxy 2. The current one is called Conda Galaxy 3, which is twice as fast. So a 64-node cluster is 8 exaflops with today's generation. So these are different places where you can find this. And where can you find our models? They're all available on Hugging Face now, which is accessible to over 5 million developers, and you can get one-click access. You can also visit the Cerebras website for access to APIs to be trying our fast inference solution. One example of how Cerebras inferencing has been used in the domain of investment intelligence. You've all heard of AlphaSense, right? The investment intelligence company. Their AI is powered by Cerebras. We're available everywhere. In terms of applications, we support Mistral, the French chat service. We have a number of ecosystem integrations, including LangChain and several others. We're working with AWS, Meta, IBM. We were Meta's partner in launching Llama 4, for example. And we have all the latest models, all powered by the fundamental building block, which is Cerebras wafer scale engine. Our uptime is to die for. It's 99.95%. It's very hard to maintain this uptime with very large clusters. The number of failures is usually proportionate to the number of parts in a system, intuitively. So if you have like 4,000, 5,000 GPUs or equivalent, and a number of network switches, hosts, and so on, the probability of failures is much higher. If you achieve the same thing with just 64 nodes in a Cerebras cluster, you have way better reliability. This is the uptime of our current inference clouds. With this, I'd like to hand over to my colleague, Gokul Ramakrishnan, who will actually give you a deep dive on how to build your own deep research agent. We will show you how you can access our APIs, get an API key, and start developing right away. Over to Gokul.
Thank you, Lakshmi. Hi, guys. With all the high throughput, low latency inference, what is it that we can possibly build? So today, I'm going to focus on a specific use case about what we can do with such high throughput inference and low latency. So I'm going to take a typical use case of building our own deep research agent. You guys must be familiar with deep research agents like the ones that you see in Perplexity and possibly ChatGPT and others. So I'm going to walk you through a simple code base that I've come up with, which uses Cerebras inference to actually build your own deep research. Before we get into AI-powered deep research, let's first look at how was deep research traditionally done, right? So if you look at how deep research was traditionally done, it all started with a research question. So people would want to, let's say, write some kind of a research report about climate solutions in the age of 2025 or something like that. So you start with a research question, and then you would want to go and peruse multiple sources, like you would go to a library to look for content, you look up some subject books, you go to Google search to actually parse through results that the internet would give you. And then you would probably engage with some market experts or like experts in the domain, subject matter experts, to get some interviews and insights from them. And then humans would take notes, and this is the most laborious process because you would actually have to take notes from different places. And then following that would be for you to compile the notes into an answer. And this is where a lot of the brain work needs to be done, right? Like if you look at the number of sources from where you need to take those notes and then distill them into something which is very, very useful, it's an extremely laborious process. And then it doesn't stop there in just one iteration, right? You will most likely miss out something, so you may have to go back again. And then you may have to do this recursively over multiple times. And this is where, deep research is an extremely recursive process. You never get answers in one pass. So you will have to keep going back and forth. Now, how does AI-powered deep research work? As you can see in the previous slide, right? The deep research process is a classic example of why AI should be applied to a use case like that. So deep research systems essentially plan and run multiple agents that search until your task is complete. Now, how does an AI-powered deep research work? The starting point will still be the same because you still have a research question, but instead of going to a library, a Google search, and interviews, you are now substituting that with a tool calling using a web search API. So in my use case, the sample code that me and my colleague Jaydeep will present to you, we are going to walk you through a simple web search using API from Exa. I think Exa is a very popular API that gives you search results from different sources, which is tailored for LLMs. But you are free to pick up any web search tool, right? Once you have the tool calling results, the next part is distilling those into context for the LLM, right? Like this is where the note-taking part comes into play. So this is done through what we call as a RAG, which I'm sure all of you are really familiar with. It's retrieval augmented generation. And using the RAG methodology, we then give the context to the LLM so that it is actually up to date with what it has to give the outputs for. And the beauty of the AI-powered deep research is that if you have a really low latency LLM and a high throughput LLM that runs really fast, you can actually do multiple passes of this really, really quickly, thereby actually enhancing the quality of your outputs and your deep research reports that you want to generate. So AI-powered deep research is actually perfect for answering complex queries, processing large volumes of material, keeping up with fast-moving fields. Like if you are asking something about AI, the field changes so quickly that it's very hard to keep up with a lot of things. So you need something that is really, that can also keep up to the pace at which the field is evolving and also be up to date with what you're trying to give it to build your deep research agent. And also to create summaries and reports. Now I have a QR code that you can scan to actually access our collab notebook. That's like the starter code that we'll walk you through. So that'll be really helpful. If you guys want to take a look at it, feel free to take a look at it. The step one is we will first install required packages. So for this, you will need to get 2 API keys, one for Exa. Exa is like the search engine that actually returns results. And the other one is the Cerebras API key. After the talk, I'll give you a QR code where you can actually go and sign up for our free tier API keys, and you can feel free to get one. But right now, I think my colleague Jaideep can show you how this package installation looks like. If we can switch to this laptop, please. Yeah. So this is our deep research agent, and this is the collab notebook. So if you see here, what I'm doing on the collab notebook is basically like I'm doing a simple pip install, and I'm giving the same API key for Exa and for Cerebras. This is my API key, so please don't use that. But then if you look at it, like once you execute the API key, it actually finishes the setup completely, right? Now, in the next set, what we are going to do is the first setup actually handles web search using Exa's auto search, right? It is really advantageous because it uses a blend of both keyword and neural search to find both exact matches and also semantic similarities. And it also returns the content of scraped URL. So traditionally, if you just scrape the URL, you will have to do a lot of post-processing to remove a lot of the tags and metadata and get only to the content. Exa actually simplifies it for you because you can use their API to get it done. And that is what the search web API does here. So this is a simple function that actually tests that like your search and content API and with your API key and everything else is actually up and running. So if we scroll down, this is our analysis function. So this function actually is the crux of your, how quickly you can generate your report. This function actually leverages Cerebras' fast inference that can analyze content and generate very useful insights. We use it for both structured JSON responses and also regular text analysis throughout our research process. So here, as you can see, this API is actually running the latest GPT open source 120B model. And this API format is an OpenAI compatible API format, if you're familiar with it. If we go to the next step, the research function is basically the crux of how you build your research methodology. As I had actually shown previously in the slides, every research function has like a query to the web search API. And following that, you want to distill that into like a context that can be given as a RAG context to an LLM. And then you want to do that repeatedly. So here, this is the main research function that actually orchestrates the entire process. So here, you call the search web, where it searches for the sources. Then it actually gets the content from the sources. And then it prepares like a research query, where you prepare a prompt. And if you see here, the prompt itself, this is our prompt, where you say that like based on these sources, please provide a comprehensive summary, 3 key insights as bullet points, and format your response in this format. And then now with this as the prompt, and with that as a context, you now ask AI what it needs to retrieve. So that's how the research function works. Now you want to add like a little more intelligence to your deep research agent, right? Like if you want to not just search for it once, but like you get the output of the results and then you feed it back again to do one more loop. So here, for example, if you have a question that says, what are the latest AI breakthroughs? You may get just random articles in first pass, but if all those articles are biased towards just one thing, in this case, let's say ChatGPT and they miss robotics, for instance, you never know what you're missing. So this is a more advanced research flow where you actually, For example, if you say what's driving the new wave of AI agents, layer 1 goes and finds 6 sources about agent frameworks. Then it reads and thinks, the AI agent reads and thinks about like, oh, all of this focus on software, but what is really enabling real-time speed? Then you go back to like the web search saying, oh, now let me search for AI hardware for real-time agents and fast inference for LLMs. And then you combine all these insights together using all the context that you've gathered so far, and then it gives you like a complete picture of what an AI agent is expected to do finally, for the final research. Now, this is the deeper research topic that I just described, and this is basically doing like a 2-layer research, like 2 recursive loops of asking for a query, distilling it, asking an LLM, passing it back to the query, again getting another set of queries, and then giving the final context from both loops to the LLM to generate your final deep research report. Can we scroll down, please? So this is the whole function that actually does this looped approach to actually get multiple queries and then eventually get the final insight. Now, this is like the final place where we actually call the whole flow. We just call deeper research topics with the topic saying, okay, let me talk about climate change solutions in 2025. We just ran it before we came. We just didn't want to, take a chance with the internet. So, but if you look at it, like what this does is in layer 1, it finds 6 sources, and then it distills that. Then in layer 2, it finds that some of the sources that it found in layer 1 also you can actually add additional context by looking at scalability and cost effectiveness of electrified net negative emissions and other things. So totally, it does 2 loops of research using LLMs and the web search API, and then it finally gives you a final summary of the deep research topic. Right? Now let me pause here and go back to my slides. So this is the EXA API that I spoke about. So this is how like EXA enables you to actually get web search results that are more compatible with LLMs. They just don't return just the page, but they also return like the content of the page, which can be passed by the LLM in a much more beneficial way. So this is the build out over what I just showed you on the code, basically. This is how like the code looks and how the response analysis looks like. Now, this is how like you can do like the basic research. So if you see here, I explained to you about how we do like 2 rounds, 2 passes of analysis. So you do 1 web search, and you use it to get the first output from an LLM, and you feed that back to web search 2, which again gives you the final answer. That's like 2 rounds of deep research analysis. Now, the bigger question is, okay, this is like a really nice walkthrough about what you can do, but how do you expand on this, right? So if you look at the Anthropic Claude or Anthropic's multi-agent system, a lot of this is actually extremely possible, and you can build your own multi-agent system if you really have fast inference in your hands. So how does a multi-agent system really look like? So you start from the same research question, but now what you do is that you split the whole search into 3 agents, which can be spawned in parallel. And with all the LLMs these days come with tool use, so you can actually use like 3 tool calling LLMs. So you can have 1 LLM sub-agent, which is actually doing some kind of web search for 1 query, 1 LLM doing another query, and a 3rd agent doing something else. And then you can combine the outputs of all of them, and then finally give that as context to the final LLM, and then eventually get to your final report. Now, if we go back to my previous collab notebook, if you can switch the screen, please. Yeah. So what is it that is so special about this? Basically, it uses intelligent orchestration with specialized agents working in parallel. So the example before this that we saw is like more sequential. So if you see, there's just 1 LLM. I'm just doing a multiple recursive loop around it. So you have a search, you analyze, again you search and analyze, and that is slow and limited. It works really well if you are limited by your inference speed or your throughput or things like that. But then, because we have Cerebras fast inference, we can afford to push the limits a little more. So Anthropic's approach is to have a lead agent. So you have one lead agent, which is, again, an LLM. And the lead agent is sort of like your arbitrator of sorts. So the lead agent says, OK, I spawn this input query into 3 sub-agents. So sub-agent 1, you go do this. Sub-agent 2, you go do this. Sub-agent 3, you go do this. And then it all comes back together. And then eventually you distill and give the final answer. Basically here, in this example, if the query is AI safety research, the lead agent breaks down the AI safety research into like 3 categories. Basically, what are the current AI safety techniques, what are regulatory developments, and what are industry implementation challenges. And each one of them is handled independently by each agent. All agents work simultaneously. That means if you are fast, they are 3x faster, so you get more broader coverage. You can actually distill information better. You have more diverse information that you can cover. And the result is basically parallel intelligence that can scale to complex research tasks. So if you scroll down, you can see the code, like how the prompt is structured. In the prompt, we say that you're a lead research agent. Break down a complex query into 3 subtasks, and for each subtask, provide clear objective, specific focus, output, and then you spawn them into 3 different subtasks. So if you scroll down all the way, right? So this is how this is the main API that calls that agent. And if you scroll further down, we can show you how the output looks like, right? Like, for example, if I'm asking for current climate change solutions, so you have 3 sub-agents. One is researching fundamental principles for climate change solutions. One is looking at latest developments. One is looking at applications in the real world. And then the lead agent takes control. So first it spawns this, and then it takes control from the outputs that is generated from these 3 agents. And then it tries to take that information together and then give you an executive summary of how this whole multi-agent system works for a detailed analysis and report. Can we switch back to the previous slide, please? So that was a walkthrough of how you can actually make use of fast inference and build your own deep research assistant, similar to what a Perplexity does or any other LLMs give you. I hope you guys can scan this starter code and build on this and build really cool apps using fast inference. I think this is going to be the future of how we can make use of LLMs in a much more useful way in terms of like learning, understanding, and generating information and perusing information in general. This QR code will give you access to our inference API keys. So please feel free to scan this QR code and then sign up for fast inference. With that, I conclude my talk. Thank you so much for listening. If you have any questions, feel free to ask.
Hey, thanks for the presentation. I have a quick question.
Yeah.
How do you guys compare Cerebras with the Grok, which I think is a competitor for you guys because they're also focusing on inference speed and inference acceleration?
So the straightforward answer is we are faster than Grok. And you can look at the artificial analysis reports. Actually, I can show you that, in fact. I don't know if Grok offers Qwen 235B, but I think this is a 235B chart, but you can go and check out artificial analysis. they have a chart of like the models that Grok supports and we support, and we consistently outbeat Grok in terms of throughput and latency.
No, I mean like, hello. Okay. Yeah, we are not talking about X, Twitter, Grok, right? I'm talking about GROQ.
I'm talking about GROQ as well.
Oh, okay,
yeah,
great.
yeah.
I just wanted to make sure.
Yeah,
yeah, because Grok now means two things.
Yeah, of course.
Okay.
Yeah.
Got it. Just a follow-up question on that. So what if I'm going to orchestrate on a multi-agent research?
Yeah.
So my understanding from you guys is like, instead of spawning a multiple LLM query parallelly, I could use Cerebras, so it could be, so instead of me going and doing a deep research in Perplexity, which spawns multiple LLM requests,
yeah.
You guys are saying if I use Cerebras, then the inference speed would be faster. But the question for me is like, so at some point of time, won't Perplexity itself will use Cerebras for their servers, or that's a question?
Yeah. Lakshmi, do you want to answer that? Oh, yeah. So the question is that at some point, wouldn't Perplexity reach out to us for?
Yes. Hear me? Can you hear me? Can you hear me?
Yeah.
So we did have some talks with Perplexity. Perplexity kind of applications can be enabled with Cerebras APIs. That is what we're trying to pitch.
Got it. So then, for time being, we would be using Cerebras directly for quick inference, but down the line, probably all these models, including Perplexity and even cloud, will probably run in Cerebras.
They can, if they want to. It provides all the APIs which are compatible with OpenAI APIs. So if somebody has been using OpenAI APIs or similar in the past, it can be converted to run in a Cerebras system very easily. Mistral, the French company, they use Cerebras. They're powered by Cerebras. The Lusha is powered by Cerebras. So it depends on how you want to use the APIs and for what application.
Got it. So if I'm going to use Cerebras cost-wise, how do you guys compare with me using cloud or?
Yeah, pricing information is available on our website. We have several tiers of pricing. We also have a free tier for developers who want to try it. We have a developer tier, and then we have an enterprise tier. So these are at different pricing and obviously different performance. We are very competitive in pricing. We are actually lower price for higher performance than most of our competitors.
Got it. Thank you.
Hello. So if you just scan that, you will get access to the page that actually gives you information about how to sign up for an API key, including pricing. So once you're in the Cloud Console, it gives you the list of models we support, the pricing for input tokens, output tokens, and all the related information pertaining to that.
Hello.
Hi.
Yeah. Hi, Gokul.
Hi.
Thanks for the informative session. Sure. If you can stay back to that slide where you are showing the case study of the traditional traditional deep research.
Yeah.
So, in traditional way, a researcher would be actually going to library or Google or newspaper or interviews to find out the relevant information.
Yes.
And you said that in case of AI powered, it will be done on the platform. That first layer would be done on the level of EXA, where it is done via web search.
Yes.
So that part I didn't understand very clearly, that if it is a web search, then why not it can directly go into the LLM and then let LLM do the same activities what EXA is doing?
Yeah, so the challenge is that traditional Google search will actually return to you links and just raw data, right? Whereas EXA actually returns to you only the content of the data.
What you just said.
Right?
Okay.
So that's the advantage of using an API like EXA. I'm sure there are others as well, but like EXA is the most
how come that other parts like library or interviews are being taken care?
So if you look at, if you have a really good API service that can actually get you up-to-date information, that is exactly what you want, right? Like some things in the library may be relative to where you are right now in terms of time. It could be old, and you may not have the most recent context pertaining to that, right? But in an LLM or in case of the internet, you have the latest and greatest information and also very relevant information that you can make use of.
Correct.
That kind of solves all of this in one go. That's how it
Got it, got it. Thank you so much.
Yeah.
Hello. Yeah, thank
Hi.
you for the nice presentation. I am from retail industry and I work for Lululemon. The use cases you talked about for fast inferencing is a very generic use case. And I'm talking in retail industry, we have real-time assortment and real-time allocation for our planning. Most of the time for the fast inferencing, your 80 to 90% time we spend in building the data context. Initially, the request is fed to our LLM system. We spend a lot of time in preparing the data, and data is not coming from one system. So what I am asking is that how Cerebras can solve before the request is sent to our LLM system, that how Cerebras can also help in accelerating the building the data context, which is basically I'm talking about your MCP, your Model Context Protocol. Yeah, thank you.
Yeah. So if you look at like EXA, that example that I showed, right? That is an example of how you can connect an external tool to an LLM. Like that is what MCP is essentially enabling us to do as well, right? It's a standard layer that can help you connect to various tools that you want to retrieve information from. So retrieving information is not really within the purview of the LLM itself. It's something that happens outside the LLM, if you think about it, right? So connecting to various sources, we are compatible. If you build an MCP application, we can definitely deploy that using fast inference on Cerebras, if that is what your question is about.
All right, thank you.
Yeah.
Hi, I think the session was really good there. The first slide was actually a wafer man showed there. So are you actually a competitor to NVIDIA over there?
Yes.
So, okay, because we don't really hear much about Cerebra. It's only NVIDIA which is like taken most of the, so I mean, where is that Cerebra lagging behind in terms of the whole competition there? We only hear NVIDIA, not the Cerebra. I know it's a little off the track question there, but yeah.
Yeah, yeah. I don't know. I mean, it's
Is the question why Cerebras is not as well known as NVIDIA?
NVIDIA.
So NVIDIA has been around for probably 15 plus years, sorry, 20 plus years. Cerebras is pretty recent. We've been deploying our clouds over the last few years, and we've made big impact. So as I showed in the presentation as well, we're way faster than NVIDIA in both training and inference. So as a new player in this market, it does, we're going through the process of expanding around the world. We've got 9 data centers, mostly in the US. We don't have one in India yet. That's probably why, you may not have heard of it. But please follow us on LinkedIn and you'll know more about us. Yeah. So the question, very good question. The question is about the carbon footprint on our data centers. A typical 64-node data center would be like 2 to 2.5 megawatts. A rack or a system is less than 30 kilowatts. So we are actually we have better price, power, and performance ratios than in GPUs. Because to power a data center which is 64 wafers, the same level of compute would take 4,000 GPUs. So that is the comparison, not one GPU versus one wafer.
Also, you risk multiple points of failure because size of the GPUs are small, so you tend to distribute a lot of things across the board. Whereas having a monolithic wafer kind of like alleviates a lot of those overheads for you.
Any edge AI based hardware that can help? I am from the healthcare ecosystem. I have my own startup, Torian Surgical, where we have a data acquisition pipeline where we have several terabytes of video data, patient records, and stuff like that. We want to build something that is on-premise for the hospitals, Edge AI stack, where we can't store their data here. So we are trying to look for solutions that are very fast and where we can store vector databases also, in addition to the AI models. And do you guys provide any hardware in that regard, or software, or any applications in that regard? Thank you.
We are open to customers setting up on-prem clouds of Cerebras. We have done that in the US. For example, GSK, GlaxoSmithKline, has got a cluster on-prem. We are expanding that. There are a few others like that. So we can talk offline on this. And we have built that model for other people.
Yeah, thank you. Thank you so much.
Okay. Yeah. There are no more questions. Thank you very much. Thanks.